everybody. We found a couple old, previously unreleased episodes sitting in sort of the archives on our computers recently, and we wanted to put them out there so you could have a listen.
A bit of a warning, they're a bit dusty.
Dusty? Really, Ben? Is that something that can happen to audio files?
Well, I just imagine them sitting in the attic or something. What I'm trying to say is the audio quality isn't as amazing as our audio quality is now, but the quality of the shows is still quite good. So enjoy. Hey, Katie.
Hey, Ben.
Deep neural nets are easily fooled. Do you know who told me that?
Who, Ben?
A paper that I've never read, but you have. Can you tell me about it?
Yeah, let's do it.
Awesome. You're listening to Linear Digressions.
Alrighty, Ben. Do you remember...
Yes?
Do you remember when we were talking about neural nets and image captioning and stuff like that?
Yes, it was using neural nets to automatically recognize objects in pictures and things in pictures, and then also create natural language captions. And they actually did a pretty good job.
Right. So today we're going to be talking about just the first half of that, just the object recognition, and a place where it can be, I think easily fooled is not what I would say, but it can be fooled in a very interesting way. And so we're going to talk about it.
Katie, the paper says easily fooled.
Yeah, well, so here's the thing, is I'm not sure if I agree with that, but I feel like my opinion is just my opinion. And I'm kind of curious to hear actually what you think, whether easily is the right word to be using here. So I'm going to tell you about what these researchers did, and you tell me if you think this is deep and profound or just a little trick. I'm honestly curious.
Cool. But first, a quick review of what neural nets are, where you've got these neurons, I'm putting that in air quotes, these little things that accept multiple inputs and an output. And the output generally is it fires or it does not fire based on the different inputs and probabilities and weightings and that kind of stuff.
And this is all a machine learning algorithm, not a literal brain.
Yes, it's modeled off of the way our brains work, but it's actually an algorithm.
Yep.
And so you have this, you can imagine it almost like in my brain, I imagine it almost like a sheet of neurons. And each neuron, within this neural net, takes in one or some numbers of pixels of a particular image that you're trying to recognize. The outputs of those neurons go into another sheet or another layer of neurons, and the outputs of those neurons go into another layer of neurons, etc., etc. And then eventually you get an output layer which spits out some kind of result.
Yep.
Whether dog or person or something completely different.
Yeah, you got it.
And the really cool thing about this is you give it a bunch of images and you tell it what the output should be, ideally. And then the computer messes around with all the layers in between. There's the input, there's the output layer, and then there are all the layers in between. And it optimizes those layers to spit out the answers that you want when given the inputs.
Or it optimizes the relationships between the layers, the weights on the connecting edges of the graph. But yeah.
Exactly. Right. Yeah. Okay, cool. So now we're talking about fooling them, huh?
Yeah, so what I'm going to do actually is I'm going to show you some pictures that were generated by the researchers in this study.
Love these. I love the picture ones.
And so they have, unfortunately, our listeners can't see them, so I'm going to ask you to describe this picture, and you tell me what it looks like.
So if you hop on the website, you can see these pictures yourself, or you can just Google for deep neural networks are easily fooled. So this first image looks like static to me.
What about this second image?
That image looks like static to me as well.
And the third one?
Static.
So the thing that's interesting about these images, Ben, is that a deep neural net says with very, very high confidence, over 99.9%, that the first image is a robin, the second image is a cheetah, and the third image is an armadillo.
They're wrong. They're wrong. That's static. Are these one of those like mind teaser puzzle things where if you stare at it for long enough, then a cheetah comes out of the woodwork?
It's so interesting that you say that, because I think that is a really interesting way of saying it. Like, maybe.
But not for our brains.
Obviously not, because I completely agree with you that this looks like I took a picture of my carpet.
Okay.
And so let me back up a little bit and tell you a little bit about how they made these images, because I think this is actually pretty cool. They were made using an algorithm that's called an evolutionary algorithm. And much like neural nets, this takes this information from biology, but now from evolution of organisms. So of course you've heard of natural selection and the theory of evolution.
Mm-hmm. The idea that in the case of biology, natural mutations from generation to generation will optimize ultimately for survival. Because the ones who don't survive, they die, they don't make babies, and those genes don't get passed on.
So an evolutionary algorithm uses this idea. You have little critters that you're simulating. So in this case, they were images. And you optimize them by some metric that you define. In this case, it's that you have a very high confidence when you put this image into a neural net. The neural net says, I know what this is, and I'm very confident in my answer. And so then you start out with something where you put it into the neural net says, I don't really know what's going on. It could be
20% could be a sticky note.
Yeah, it could be any one of 100 different things, but then you start to make the little mutations on the picture, and some of these mutations will move it towards a more and more confident response from the neural net. And then once it gets above some threshold that you can set, then you say, this is one of my cases. Now, this is one of my images that I've generated for myself that can fool the neural net.
That's really interesting.
Yeah, I think evolutionary algorithms are super cool.
Yeah. Well, the idea of evolution is super cool. Of course, that applied to algorithms is even more cool. Uber cool.
So that's what they did here. They did it in a couple different ways. You can see that some of them are just random noise. Some of them, they also tried to impose certain symmetries on them so that you get patterns in them. Because
this wavy one with orange and blue wavy things, and it says starfish.
Yeah.
And it looks like a pattern that you'd put on wallpaper or something.
It does a little bit. Although with this one, if you squint, you can see that there's got sort of the blue in it and the orange that you could imagine seeing in a picture of a starfish or something.
Okay. Also, if that was wallpaper, I wouldn't want to spend time in that room. That's very noisy.
It would give you a headache.
Mm-hmm.
So as they go through the paper, they talk about some of these examples where they say, like, okay, I would never identify that as a starfish. But some of them, you look at it, you say, like, oh, okay, maybe I kind of get where the neural net is coming from in identifying this as a starfish.
Yeah. But the one that looks like a freight car, it doesn't look like a freight car at all. It looks like this weird black platform with this pink and green kind of circular tie-dye noise and a gradient going to white in the top. It's just like completely, clearly not a freight car.
Yeah, there's no way a human would make these particular set of mistakes.
Yeah.
And so when I was reading this paper, I'm a little bit torn. On the one hand, I think it's really interesting and maybe very profound, but I'm curious to hear your opinion on this, that a computer can make a mistake like this, right? We would consider this such a fundamental mistake that you can just take a picture of what looks like noise, and for some reason that just happens to light up the right combination of neurons in your neural net that it says with very high confidence this is the thing.
Well, here's what I would like to know. Whatever this algorithm is that's identifying these images, if you gave it 100 times the amount of training data, would it make fewer of these mistakes? My guess is probably yes. It would probably be better able to narrow in on what makes a robin or a cheetah a cheetah.
So in fact, they actually poke at that a little bit. So they look in particular at cats and dogs. So you have, as it happens, the training corpuses, the pictures that they had lots of pictures of cats and dogs, just more of those than other types of images.
Yeah.
So you can actually do a test like this. And you say, is it better at cats and dogs than it is at other types of objects? However, as it happens, the cats and the dogs are split across many different classes in the training set that they have. So it wouldn't just say dog, it would say golden retriever, beagle, cocker spaniel. So you have both the high statistics issue and you also have the case that it's spread over several different classes, several different labels that all describe dogs. And so between the two of those, it can be actually a little bit tricky to unpack whether having more data in this particular case, they see a better result, but maybe that's because there are more types of dogs rather than just more examples of dogs overall. Another thing that they try out is so you don't feed these garbage images in when you're training. So it's a little bit, you could make a very strong case that it's unfair to give it something that it's never seen before and it's like so different from anything it's ever seen.
Yeah.
Which, if it's never seen it before, then probably it shouldn't be returning a very high confidence. So, that doesn't completely, cut the legs out from under this. But they did try a version of the algorithm where they would train it. Then they would use the misclassified noise images in the next version of training to see if it made the same mistakes over and over again. And it did learn from its mistakes. It could make new mistakes that are exactly like the ones that it made just now. But it did learn with this specific random pattern of noise. This is not, in fact, a cheetah. This is just random noise. So it doesn't learn in that respect.
So I think I have two thoughts about this. One thing I have to say about this is it seems that by using algorithms to find the exact weak spots of particular algorithms, there's something about that seems kind of unfair if I'm anthropomorphizing the neural network.
You're absolutely cherry picking your inputs here. Yeah.
Yeah. But it's also really fascinating to me that these algorithms can be, I guess, hacked in a sense in this way. They can be manipulated and fed this exact perfect kind of input that results in them being completely and profoundly wrong. And the second thing that I think is really interesting about this is that as these technologies, say image recognition, progress, we're going to start relying on them for things that actually matter. Right now, we're relying on them for tagging your Facebook friends. All right, so who cares if it thinks that my dad is my brother? I don't care. It's, maybe a little bit funny at times, but if that system fails, that's okay, right? If Google Street View fades out a telephone pole instead of a face, that's okay.
Yeah.
But the better these algorithms get and the more we start to trust them, the more we'll use them. And then we'll actually be vulnerable to specific kinds of attacks like this.
There are a couple of things that they mention in this paper. It doesn't go into as much detail, so I would be really interested to see if I can find out more about this. But they give a couple examples. One is if you're trying to do, for example, photo ID of a person. That there's some kind of face scanning mechanism to figure out if you have whatever authorized access to a certain place, or it takes a picture of you with the camera to verify that you're the person who's sitting at a computer to allow you into a certain account. That if you could just put up the right set of noisy pixels, that you could fool it. So it's like jujitsu, where your opponent's, your opponent can be very, very strong, but if you know their exact weak spot, you can pinpoint it and just flip them completely over.
Now, what's interesting is my first response in my brain hearing you say that is, no, that wouldn't quite work because you could just take a picture of yourself instead of showing it noisy pixels or da-da-da. So, I'm already thinking in a very limited way. I'm thinking, no, that'll be fine. That would never be able to be a successful attack. But the thing about security is people can compromise your system in ways that you would never predict. And that's exactly the point. If you don't predict the ways in which the system can be compromised, you can't prepare for it. So us trying to talk about ways that these systems could be compromised and then cause, say, a misauthentication of a user, and then someone's personal data gets out or something like that, it's kind of silly. We're still years away from that probably actually happening, but I definitely see it as a potential weakness.
Yeah, so I'm glad you like this paper. I kind of liked it too, but again, I'm still trying to wrap my head around it. I think there's a lot more in it, but we've been going for a little while now, so I would just recommend to our listeners, if this has been interesting to you, it's a very approachable paper. A lot of
it is.
Neural net papers have lots of math in them. This one is very clear, lots of pictures, and there's some more interesting things that they're thinking about in here that we just don't have time to get to today, unfortunately. But anyway, clearly our enthusiasm about neural nets remains.
Mine certainly does.
But I wouldn't say that we have algorithms now that we fully could say with confidence that they always do what we think they're going to do, right? They can still surprise us.
Linear Digressions is a Creative Commons endeavor. which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.